All right, welcome to the second video on the review. This will be section 4. Due to a printing error, there's two different sections labeled section 4, but I'll be doing them both right here. The first one is direct and inverse variation. So the first problem is assume that y varies directly. And the key thing here is it says direct variation. And that's the equation for direct variation. K is the constant of variation. So this is easy enough. If when y equals 5, x equals negative 5, what is k? Well, we're just going to divide both sides by negative 5. And we'll get k equals negative 17. So negative 17 is the constant of, I hope I can spell, variation. Okay, this next one. Y varies directly with x. Y equals k times x. If y equals negative 48, when x equals negative 6, that's the first part we want to do. So the first thing we want to do is use that first data pair they give us and find k. So we'll divide both sides by negative 6. And you'll get k equals 8. So the direct variation equation for this particular problem is y equals 8x. Now that we know that, we can do the second part here, which is what is the value of y when x is 4? Well, y equals 8 times 4. So y equals 32. So 32 is the correct answer. So this one, it says y varies inversely. The equation for inverse variation is y equals k divided by x. Assume that y varies. Okay, so what is the constant variation? So we plug in negative 10 equals k over 4. Just going to multiply both sides by 4, and I'll get k equals negative 40. So the constant of variation is negative 40. Assume that y varies inversely as x. If y equals 6 when x equals negative 1, what is the value of x when y is 12? So first thing we're going to do is we know that y varies inversely. Y equals k over x. Then they give us a data point. So 6 equals k over negative 1. Multiply both sides by negative 1. And I'll get k equals negative 6. So the specific one for this equation is the specific equation, inverse variation equation for this is y equals negative 6 over x. And then they give us a second data point, which is what is x when y is 12. So 12 equals negative 6 over x. So to solve this, I'm going to multiply both sides by x. And I'll get 12x equals negative 6. And I'll divide both sides by 12. And I'll get x equals negative 1/2. And there's your answer. What is the value of x when y is 12? X is negative 1/2. Point A is an element of a direct variation. Plot or draw 2 points other than A that are also elements of this direct variation. Now, one of the key things to remember is that a direct variation always goes through the origin. Oh, whoops, did I misspell it? Sorry. Goes through the origin. I don't think I spelled origin right there. That's why I teach math. And I erased it. So that's the origin. Now we can see that the direct variation is the slope is constant, so it'll be up 3 over 1. So I'm going to call that B. And then if I go up 3 and over 1, we'll call that C. And there are my 2 points. Determine if the graph is a direct variation. Well, it goes to the origin, so yes. It is, yes, it is direct variation. Then determine the slope of the graph. So I just need to pick another point on the graph. The rise, remember slope is always rise over run, so this will be 1 over 2. So the slope is 1/2. The amount of time it takes to build a shed varies inversely. With the number of people working. If it takes 8 hours for 5 people, then K will be 40. So my specific variation equation for this is y equals 40 over x. How long will it take for 3 people to build a building? So that'll be y equals 40 over 3. And the answer will be 13 1/3 hours. Or if you prefer, 13 hours, 20 minutes. Next problem is more the same. Varies inversely. So y equals k over x. So if it takes 5 hours for 2 people, then k equals 10. So then y equals 10 over x. How long will it take 4 people? So that's y equals 10 over 4. So y equals 2.5 hours. Or 2 hours, 30 minutes. Now for this problem, I'm going to actually cheat a little bit and just make sure we understand something, is that direct variation says y equals k times x. This is direct variation. Inverse variation says that y equals k divided by x. But if I solve these for k, because it's a constant, it doesn't change, then y divided by x, k equals y divided by x in direct variation. And in inverse variation, x times y equals k. So this is really, when you're looking at a table of values, how you want to go about this type of problem. I'm sorry, I'm getting ahead of myself. That was how you do j and k. I apologize. So for these, we're just looking for those direct and indirect variations. So this, you see the squared, that's an either. Y equals x, right? That's direct variation. Y equals 2/3 x, that's still direct variation. Here, we see the x in the denominator, so that's obviously inverse. And here we see that x times y, which is what we saw right here. So that's E. This last one, this +1, means it has a y-intercept of 1. It doesn't go through the origin. And so that's that one. So here, determine if this. So here's what I want to do is, what is x times y is 24. Here, x times y is 96. And this is x times y. This and this are not the same. So this is not inverse variation. How about if we do y divided by x? Well, 6 divided by 4 is 1.5. 12 divided by 8 is 1.5. 18 divided by 12 is 1.5. And 27 divided by 18 is 1.5. This is a constant for this. And if we go back, y divided by x being a constant was direct variation. So this is direct variation. So let's try this one. Let's try x times y. Well, that's 8, 8, 8, and 8. X times y, if that's constant, then that means that y equals k divided by x, so that's inverse variation. All right, so now we're going to move into the scatter plot and line of best fit. For this one, you're going to have to use the calculator. Now, as a stats teacher, I'm probably going to teach this maybe a little bit different than your Algebra 1 teacher did. And that is that as a stats teacher, it's kind of against my religion to put the data in as it's presented. So I'm going to do 5, 6, 8, and 10 instead of 19, 0. And I'm going to label this, instead of X, I'm going to label this as, oops, sorry, years since 1900. And I'll show you why that is in a second. And really, you should do this whenever you do something that contains years. And I'll show you why in a second. And so then my other values I can enter just in 47.3, 50, 54.1, and 59.7. Whoops, sorry, 59.7. So then I should really make sure, want to look at the data. And there's my clearly a linear pattern. So I am just going to go stat, calculate the line of regression. Now I'm going to do a little fancy trick here, which is I'm going to store it in the calculator as well. So here's my equation, and this is going to disappear. Now, you shouldn't round to the very end, but at the very minimum, we should write out to 3 decimal places. So this will be y equals 2.429x plus 35.166. Now, if you didn't rescale, if you had entered 1905, 1906, 1908, 1910, then your equation is going to come out as the exact same slope, but your y-intercept is now negative 4,579.580. Now, the slope, when you do these kind of problems, means the rate of change. So that means for every year that the later you were born, your life expectancy was going up 2 years. The problem is that this is the life expectancy in the year 1900, 35 years old. This is the life expectancy in the year 0. I don't think anybody's going to be negative 4,579 years old. The real reason that this is a problem is that if you only went to 1 decimal place, this number is going to be so large it's going to completely screw up your prediction in number 2. So in number 2, what you would do is I'm going to use my equation. Now, since I did year since 1900, my equation is y equals 2.429 times 50 plus 35.166. And if you put that in, you should get a life expectancy of 156.616. Now, you're going to say, wait a second, someone's not going to live to be 156. And that is correct. And this is also a very nice illustration of the problem with extrapolation. If our data set is from 1905 to 1910, and we're making a guess about 1950, we're making a guess way outside our data set. And let me just bring back up the graphing calculator again. and just give you an idea of what I'm talking about, is that if I graph my line, which we'll see gives me a very nice fit, well, this first point here, that's 1905, that's 1906, that's 1908, and there's 1910. Well, think about where 1950 is. It's going to be way out here on the map. And so we're making a guess that's way outside our data set. You should always be very, very, very careful if you do that. All right, so for this next problem, is it asks you, so you want to kind of draw your own line in, just kind of like that, through your data set. About how many people would go to the beach when the temperature is 90 degrees? Well, 90 degrees is right here, so I'd go up on my line and I'd come over and I'd get something around here. So my guess would be 380, and so what's our best guess? Well, clearly the answer is going to be C. This problem I'm not going to do. There's a problem down here with the answers. We're skipping that problem. For this problem, we're going to once again have to enter the data in the calculator, which if you don't have at home, you're kind of out of luck. And then use that line of prediction, and you should get a bowling score of 179.76. If you have questions on how to do this, you're going to have to bring in a calculator and go over it with your teacher. So, sorry, that's the next section. So that's this section. That's section 4 of both section 4s on inverse and direct variation and line of best fit for the quarter review.